Hi, my name is Satoshi Hoshino from Utsunomiya University, Japan. In this movie, I'm going to talk about CNN-based motion planning for object storage by dual-arm robot. Actually, this was presented in IEEE SICE International Symposium on System Integration 2025. Okay, this picture shows a dual-arm robot next stage equipped with an RGB camera on the top. So RGB images are used as inputs, and outputs from a motion planners are hand positions. For these image inputs, we have so far proposed a motion planner based on CNN and Pascal CNN. And this motion planner was trained through motion instruction and imitation learning. As a result, the robot determine the targets from the multiple objects on the desk, as you can see here in these pictures. So by feeding these target object images to the reaching motion planner, the robot successfully grasped the target objects. Okay, so in this movie, we further focused on the strange motion of the grasped objects onto a shelf after the reaching motion. Okay, here let me explain the challenges in object storage motion planning. Robot is first off required to detect storage space um, in the shelf, in which is the center one in this picture. After that, the robot moves the hand toward the respective target spaces depending on the detected results. Moreover, compared to the reaching motion, the robot moves the hands toward the depth direction for 2D images, as you can see here in these movies. So we use additional inputs to the motion planner. However, due to these multimodal inputs, image features which are pretty much important to determine the motion outputs might vanish in the convolutional processes. In consequence, the robot cannot plan the motions while paying attention to the visual information. So we propose the following approaches for the object storage motion planning. Okay, now from the robot storing the objects, these RGB images are first captured. So after that, segmentation and detection images are generated through instant segmentation. The segmentation images are used as inputs to a hand state classifier. So if the hand state is classified to close to keep clasping, the segmentation images are again used as inputs to the motion planner. And in addition to these images, goal directions calculated from the detection images are used as input. Moreover, kind hand positions are also used as input. And for these multimodal inputs, next hand positions are determined as the motion output. So the robot moves the hand by solving the inverse kinematics using move it. On the other hand, if the hand state is classified into open to place the objects, then the robot finishes planning the motions. For the image features vanishing in the motion planner based on CNN, we apply shortcut connections to the convolutional layers. Okay, so let me explain the goal direction and the motion planner in more detail. As for the goal directions, here let me show you an example of the shelf composed of three spaces. In this image, the spaces and objects and hands are all detected as shown by red bounding boxes, and the bounding boxes corresponding to the center space and this left object, the coordinates of this bounding boxes corresponding to the center space and the left objects are indicated by the white points. So first off, the center coordinates of the pressed objects are calculated. For example, the center of the left object, OB1, is calculated as you can see here. So by comparing the objects and the spaces, the robot can see that the objects are placed in the center space. Okay. In other words, there are no objects placed in the right and left spaces. So these are the target spaces for object trace. In the same way, the center coordinates of the three spaces are calculated. So by comparing the centers of these spaces, C1 is assigned for the left hand and C3 is left for the right hand in order for the hands to avoid collisions. And finally, the center coordinates are used as input to the motion planner as the goal direction. Okay, this motion planner is based on the CNN for image input. So as you can see here in this structure, in addition to the image inputs, the current hand positions and the goal directions are used as multimodal inputs. However, due to these multimodal inputs, it is sometimes difficult to extract image features which are important to determine the motion outputs. Here, let me show you an example of the image feature vanishing. For the image input, this figure shows a feature map which was extracted in the last convolutional layer, but unfortunately, we cannot see anything in this map. Because this unclear map is fed to the following fully connected layers, the robot cannot plan the motions while paying attention to the hands, objects, and shelf. Okay, so in order for the CNN to clearly extract the image features from these multimodal inputs, we apply the shortcut connections to the second, third, and fourth convolutional layers. And by skipping the following convolutional layers, it is possible to prevent the image features from vanishing. Okay, for imitation learning, first off, storage motions are instructed by an expert operator. For this purpose, these three environments, depending on the position of the place the objects were prepared, and the storage motion is indicated as you can see here in this movie. And during the motion instruction, the robot registers the multimodal inputs and instructed motions, which are the next hand positions. In doing so, the training dataset, as you can see here, is collected. So this dataset is then used for imitation learning. In this phase, the CNN is trained by minimizing the output loss, which is calculated by the following mean square errors. Finally, through imitation learning, the convolutional filters and connection weights are optimized using ADA. Okay, for object storage experiments, a dual-arm robot equipped with Azure Connected DK is used, as you can see here in these pictures, and the robot stores the objects onto the upper shelf, which is divided into three spaces, AL, AC, and AR. For example, in this environment, two objects are already placed in space AR, so this environment is referred to as AR. For comparison, the following three motion planners are applied to the robot. In the first one, shortcut connections are only applied to the convolutional layers. And the second one, goal directions used as input in addition to the current hand positions and images. And in the third one, both the shortcut connections and the goal directions are used. Here, let me show you the results of the experiment. As for the first motion planner, unfortunately, the robot failed to store the objects in all the environment. The robot based on the second motion planner succeeded in storing the objects in only in environment AL. In contrast to these motion planners, the robot based on the third motion planner succeeded in storing the objects in all the environments. So here, please have a look at the movies from the robot's point of view in environment AC. First off, the robot based on the first motion planner, we can see that the hands stopped moving before the shelf. The robot, based on the second motion planner, moved the hand toward collect target spaces, but after that, the grasped objects collided with the shelf. On the other hand, the robot, based on the third motion planner, moved the hand toward the collect target spaces and succeeded in storing the objects without collisions. For these results indicating the effectiveness of the third motion planner, we here first focus on the hand trajectories of the robot depending on the first, second, and third motion planners. First off, from these two left figures, we can see that the robot, based on the first motion planner, stopped moving the hands before the shelf. And in the rightmost figure, we can see that the robot moved the left hand toward wrong space where two objects were already placed. On the other hand, the robot, based on the second and third motion planner, moved the hand toward the collect target spaces. So these results indicate that the goal directions were useful inputs for object storage motion planning. So here we further focused on the feature maps extracted in the second and third motion planners. For example, for these two image inputs in the feature maps of the second motion planner, we cannot see anything. On the other hand, in the feature maps of the third motion planner, we can clearly see the hands, objects, and the shelf. And so these image features clearly extracted by applying the shortcut connections to the convolutional layers enable the robot to store the objects without collisions. Okay, in this movie, we propose a CNN-based motion planner for object storage by a drum robot. And the proposed motion planner enables a robot to store the objects not only in instructed environment, as you can see here, but also in unknown environments where storage motions were not instructed, as you can see here from the bottom movies. Okay, that's it. Thank you for watching.